We were talking at the end last time about Euler circuits. This is the first kind of graph theory problem that we're talking about in detail. An Euler circuit, remember, is a path starting and ending at the same point, the same vertex. That's what circuit means. A path starting and ending at the same vertex, which uses each edge once. I'll say exactly once. It covers all the edges, and it does not hit any edge more than once. All right, that's called an Euler circuit. It's named after this guy Euler. It's a path starting and ending at the same vertex, which uses each edge exactly once. So, for example, if I have something like, I'm going to make a cute little bow tie kind of thing, and then maybe also put a edge there, and then maybe I'll double up these guys. How about that? Here's a graph. Does it have an Euler circuit or not? Can you actually do this, what I described? Start and end at the same place, and hit cover every edge exactly once. So you have to use every edge. You can't repeat any individual edge. I think actually this one does have an Euler circuit. This one has an Euler circuit. E-circ. Can you draw it? Maybe. You know, we're going to talk in more detail about how exactly do you know if it has one or not, and then if you have decided that it does, how could you actually draw one? These are all different questions, but I already know kind of how to do these things, and I'm just trying to demonstrate the concept here. I'm going to try to draw one in starting at this point. Let's say I come down here. As I'm drawing this, I'm going to draw it sort of next to the original lines. Otherwise, it will be very difficult to tell what I'm talking about. But let's go across here maybe up here, down there. How am I doing so far? I think I'm doing all right. Back this way and then up there. I think I did it. I covered every edge once without repeating any edges, all right? This is an Euler circuit. And this is the kind of thing that we're going to talk about over the next few times. First of all, how do you tell if it's even possible or not? It turns out there's a very easy way to tell if it's even possible or not. And we're going to talk about that today. And then furthermore, once you know if you know that it is possible, how do you actually figure out how to draw it? That's another question entirely, and that we're not going to get to today, but we'll talk about eventually. All right. This one has an Euler circuit, but it's not always possible. For instance, if I just took this bow tie shape without the rest of it, is there an Euler circuit in this one? So can you start over here and cover every edge and come back to where you started? I think this one actually, I would say that can't be possible in this one. Can anyone give some kind of a reason, explanation? How do you know that's not possible? I see some people shaking your heads. Yeah?
Well, you have to go over the middle line twice.
Yeah, right. If you want to start over here on this vertex over here, you have to eventually cover these edges, and so you'd have to use this edge once to get over here. But then you have no way of getting back. So this one actually, this has no Euler circuit. And somehow it has to do with this edge right there. I will say because of this, there's actually a name for this. An edge like that is sometimes called a bridge, because that is the only way you can get from this side to this side, right? And the fact that there is an edge like that, which kind of, this edge by itself sort of splits the whole thing into two parts. There's the one on the left side and the one on the right side. It means if you ever go across that edge once to get to the other side, there's no way to get back to the other side, to the first side, right? So this one here has no Euler circuit. It's basically because of that edge right there. Although this can happen even in a less obvious example, something like this. If I make this kind of thing, all right? That one also has no Euler circuit. You can just try and play around with this. If I start up here, maybe I try and go like this, come back here, up there, down there. I'm going to get stuck eventually, right? This now, the fact that I just tried to do it and got stuck, that doesn't mean it's impossible. But actually, I happen to know that it is impossible here, although for less obvious reasons. So this one is also has no Euler circuit, but this one I would say is less obvious. Exactly why, it's hard to explain exactly why, but it's true in this case. You can't do an Euler circuit in there. All right? But it turns out, and our main sort of thing to talk about for the day, there is a very easy way to just look at a graph and immediately tell whether there is or is not an Euler circuit. And before I get to that, so I will just say, Euler figured this out, how to tell if an Euler circuit exists. This is why it's named after him, because he proved the theorem that says the Euler circuit exists when this and this and this. And it's easily identifiable features of the graph. Before I tell you about the theorem, I want to just talk about a completely unrelated, not unrelated, but it's a bit of mathematical terminology which is not specific to graph theory. I want to talk about this magical little phrase, if and only if. You may have heard these words, these four little words in a math class before. I don't know, depending on how technical your teachers were trying to be. If and only if. This is a phrase in mathematics which comes up a lot. This is sometimes written as if with two F's. When you see if with two F's, that means if and only if. And it is similar. This phrase has a similar meaning just to the ordinary word if, but it means something a little bit more specific. So if I say something like A, if and only if B, so that if with two F's is if and only if B. This means we say this when A and B are logically equivalent. All right, the A and the B in that case, if you say if and only if, it means that those two things that you're describing are the same as each other, logically speaking. Logically the same as each other. All right. Another way to kind of deconstruct this is you could say A if and only if B. It means, logically speaking, if A, then B, and if B, then A. It means if the one thing is true, then automatically that means the other is true. And also, if the other is true, then automatically the first one is true. So, for example, a proper usage of this this phrase, if and only if, I will say, e.g., I could say something like, I am a parent, if and only if I have a child. All right? Those are equivalent to each other, aren't they? What I mean by this is, it means that if I'm a parent, then that's the same as saying that I have a child. And also, if I have a child, that's the same as saying that I'm a parent, right? Is that actually correct? I think that is actually correct. I hope, don't at me on Twitter. This is the kind of thing that people argue about, I think, about. I don't know if I'm being insensitive to someone who, I don't know. Is this someone whose kid died, maybe? They're still a parent? Can you be a parent if you don't have a child? Maybe. I'm not trying to get into that, right? I respect all people who want to call themselves parents for various reasons. In the ordinary way that we talk about these words, being a parent is the same. It means that you have a child. Those are the same thing, right? And it's not just that one means the other, but also the other one means the first one, okay? That's what is meant by if and only if, all right? I actually saw someone, I don't know if you saw this, I think this was maybe a viral tweet like a few days ago. They said it's deeply insensitive when you're talking about somebody's children to refer to them as kids is offensive, because a kid is a young goat. And she's like, don't call my children kids. All right. I apologize if that's insect. I do refer to my own children as kids. I don't have a problem with that. Okay. Let's talk about. So I just got a whole bunch of other examples. Are these correct? Here's one. How about I am old enough to drink? If and only if, let's just say, like, according to the laws of the United States, if and only if I am 35 years old. Is that a correct usage of the phrase if and only if? Remember, if and only if means that these two concepts are equivalent logically. They are the same as each other. What do you say? Yes or no? I see some shaking heads. Yeah, this is actually not an appropriate usage of the word if and only if. That's because, remember, it means both of these things, right? It means if A, then B, and also if B, then A. Now, in this case, if I am 35 years old, then I am old enough to drink. That's true. But the other way around is not true, right? If I'm old enough to drink, that does not necessarily mean that I'm 35 years old. So, sort of, this is like half true. But you would not use the word if and only if in this context. How about, I got a few more here. How about I have seen Lucas the Stag, I mean like the guy in the suit, if and only if I have been to Fairfield University. Is that true? You want to think of it in these like two parts. Is it true that if this one is true, that means this one is true, and then also is it true if this one is true, then that one's true? I think actually in this example, probably neither of them is true. Like, if I've seen Lucas the Stag, that does not necessarily mean that I've been to Fairfield University. And if you've been to Fairfield University, that does not necessarily mean that you've seen Lucas the Stag. So this is definitely a wrong usage of the word if and only if. How about this one? Some number, this is more mathematical. X is even, if and only if x is divisible by 2. Is that an appropriate usage of if and only if? I say yes, it is. Those two things are actually the same. When you say x is even, that means exactly the same thing as x is divisible by 2. In fact, that's kind of the definition of what the word even means. All right, so this is a correct usage of the word if and only if. How about x is Mark Nemec? You know that guy? If and only if x is president of the university of Fairfield University. Is that accurate? What the question is, are these actually logically the same thing? Being Mark Nemec is the same as being the president of the university? I mean, like right now, we have had other presidents in our past, but I'm talking about right now. Actually, this is somewhat debatable. Does anybody I see a lot of people saying yes, this is true. What it means is if someone is the president of the university, then they are Mark Nemec. I think that's definitely true. If someone is Mark Nemec, then they're the president of the university. Is that true? I mean, maybe, are there other Mark Nemecs? I imagine there might be. I don't know. So I would say this is true if there's only one Mark Nemec. Mark with a C. Am I right? I think that's correct. There could be other Mark Nemecs, maybe Mark with a K. So I would say this is correct, assuming there's only one Mark Nemec. Only one Mark Nemec exists. All right. If there are other Mark Nemecs who are not the president of the university, then this would not be an accurate statement. Okay. I'm just trying to impress on you what this word if and only if means. It's actually a very strong thing. It means you're saying that two things they actually mean exactly the same thing. All right. Like for instance, x is even if and only if x is divisible by 2. That's when you would use this phrase, if and only if, when the two things you're saying mean exactly the same thing. Another one which would be correct is this. This is a little more interesting. X is even if and only if x plus 1 is odd. That's also true. Because it is true, if some number is even, then that number plus 1 will be odd. And also, if some number plus 1 is odd, that means the original number will be even. So this is another proper usage of the term if and only if. All right? All of this, I'm just trying to explain exactly what I mean when I say if and only if. It's a very, sort of logically speaking, it's a very strong thing to say. You are saying two things are exactly the same logically as one another. All right? If you make mathematical statements like this, they can be fairly deep because you're saying two perhaps different ideas are actually the same idea. All right? Anyway, here's I want to tell you about Euler's theorem about Euler circuits. Euler actually is super famous, and there are many things named after Euler, and there are several things called Euler's theorem, but I will just call this Euler's theorem about Euler circuits. It tells you when an Euler circuit exists or not. Here it is. A graph has an Euler circuit if and only if what I'm about to write is equivalent to having an Euler circuit, and actually what I'm going to write is very easy to check if you're looking at an example graph. All vertices have even degree. It has to do with the degrees, and that is a very simple thing to check. There's something actually kind of deep and powerful about this theorem, kind of cute, I would say, because if I show you a graph and ask you does it have an Euler circuit or not, on the surface that's a very complicated question to answer. You have to look very carefully, see are there any like bridge type edges or something like that. But it turns out actually the whole question can be answered with this, which is much simpler. All right, the if and only if means these two concepts are the same logically, even though the one on the left I would say on its surface it seems very complicated, whereas the one over here seems very simple, right? That's why I would say this is a powerful and kind of deep theorem. Okay, for example, let's just do a whole lot of examples. This one here, does it have an Euler circuit or not? The answer is it does not, because you look at the degrees, right? I'll write in the degrees. Remember the degree of a vertex is just how many edges touch it. So this one is a 2, this is a 3, this is a 2, this is a 3. It has no Euler circuit because it has some 3's there, right? Euler circuit is only when they are all even. And if you see any odds, that means it does not have an Euler circuit. How about something like, this is a weird looking one. How about that? Does this have an Euler circuit or not? All you got to do is look at all the degrees. I'll just write them down. This is a degree 2. This is a 2. Remember, the degree is just how many edges touch that vertex. The one in the middle is a 2. This one on the right side, how many is that? Whoa, sorry. Over here? Looks like 4 to me. You are counting how many edges touch the vertex. It's 4. And the one on the bottom, also 4. So that one actually does have an Euler circuit. All right? It's very easy to tell if it does or does not. Now, if you want to actually draw it, that's another matter. But the theorem doesn't tell you how to draw it. It just tells you, does it exist or not? How about something like, I'll just make a big graph like that, where every crossing is a vertex. Does this have an Euler circuit or not? You want to look at the degrees and see if there are they all even or are there odds? No. You see an odd?
Yeah.
Where's an odd?
The middle left is 3.
Sure, like right there, that's a degree 3. So right away you can tell there's no Euler circuit here. All right. How about this? This should look familiar if you remember anything from last time. This is the graph corresponding to the 7 bridges problem, which is what got Euler thinking about all of this stuff. Does this have an Euler circuit or not? You just look at the degrees. That's a 3 right there. So the answer is no. No Euler circuit. All right. This is a 3. This is a 3. I guess over here is 1, 2, 3, 4, 5, right? So in that one, actually, they're all odd. But anyway, there is no Euler circuit because they're not all even. All right? The theorem is super easy to use. It just boils down to the degrees. This one thing to say about this is what we call an existence theorem. That is, it only tells you if something exists or not. It doesn't actually tell you how to find it if it does exist. So, for instance, this example here, you can tell that there is an Euler circuit. The Euler's theorem doesn't actually tell you where it is. It just says there is a Euler circuit. But that's called an existence theorem. Mathematicians generally like existence theorems. People like engineers don't always like existence theorems because an engineer, it's not good enough for them to know that something could possibly exist. They actually want to make it or find it or something like that. But mathematicians often are satisfied with existence theorems. You want to hear an awesome math joke about existence theorems? You ready for this? This is one of those jokes where it's like one thing happens and it's like two people react in a normal way and then the third person reacts in a weird way, and that's what makes it funny. You know what I'm talking about? I'm telling you the structure of the joke. This is the logical structure of the joke before I tell you the joke. So it's something like there's a physicist and an engineer and a mathematician, and they are staying in a hotel in their own separate rooms overnight. And you know, they get to the hotel room and it's got like the bed has like all these extra hotel blankets on it. When the physicist gets there, goes to sleep, like throws a bunch of extra blankets on the floor, gets like the ice bucket before they go to sleep. And then they wake up in the middle of the night. The physicist wakes up and discovers that the bottom of the bed is on fire. And the physicist is like, oh no, what am I going to do? Picks up the ice bucket, dumps the ice bucket on the fire. It goes out, and then it goes back to sleep. Everything's fine. The engineer finds himself in the same situation, gets up in the middle of the night, and the bed is on fire. The engineer decides to pick up all the extra blankets and like smother the fire. The fire goes out, everything's fine, goes back to sleep. You ready for the funny part? This is going to be hilarious. The mathematician in this scenario gets up in the middle of the night, the bed is on fire. The mathematician looks at the ice bucket, is like, okay. Looks at the blankets on the floor, is like, okay, a solution exists, and then goes back to sleep. You get it? The point of the joke is mathematicians, sometimes all you get is this existence thing. All you know is there is some solution, but the mathematician doesn't always care about how you actually figure out what it is, only that it exists. All right? I want to explain a little bit about why this is true. Why should you believe that the degrees being even makes an Euler circuit? So why? I don't want to go through a big proof of this. Why it's true. Why is it true that Euler circuit has something to do with degrees being even? All right, I would like to kind of, I just want to give you the basic idea. Let's imagine I have a vertex somewhere in my graph, and I'm going to sort of zoom in on this one vertex, all right? I guess I could have drawn it bigger, but I decided to draw it small and then zoom in. You have the rest of the graph elsewhere on this picture, but let's just imagine that you have a point, and I'm looking closely at one point. If there is an Euler circuit in this graph, usually I draw the Euler circuit in red, right? If there is an Euler circuit, it has to at some point arrive at this vertex and then leave again on one of these other edges, right? And then it goes around the rest of the graph. But the Euler circuit has to cover every edge. So eventually that Euler circuit will come back here, maybe to cover this edge, and then has to leave again, and then goes do some other stuff, and then maybe it comes back in here on this edge, and then it has to leave again, right? Now, everything worked out great in this picture. It worked out great because this vertex had even degree. The Euler circuit, near each vertex, it must arrive on one edge and leave on a different edge, all right? And if you're actually going to cover all the edges, That's only possible if there's an even number of edges here. If there were an odd number of edges, you would somehow get stuck, either on the inside or on the outside. So the moral, or the basic idea here is we need to arrive and leave along different edges. Right? And if the number of edges there is odd, if the number of edges is odd at this vertex, then we'll get stuck. For example, if you had a vertex, I'm going to draw a similar picture again, but with an odd number of edges, say 1, 2, 3, 4, 5, 6, 7, right? In this case, the Euler circuit maybe comes in here and then leaves again that way, and then it does some other stuff, and then comes back, and then leaves this way maybe, and then maybe comes back here, and leaves that way, and then maybe comes back here. Now you're going to be stuck because there's no edge that you can use to leave anymore, because you're not allowed to repeat any edges. So the moral of the story is an Euler circuit will get stuck if there's any vertex with an odd degree. So if the degree is odd, the circuit gets stuck. That's the basic idea, and I don't want to go into any more detail than that. If the degree of any one of the vertices is odd, then your Euler circuit is not going to be able to arrive and then leave again in the proper way. It will end up arriving, but then it will have no other way to leave. All right? It's all about leaving and arriving. All right? Excellent. I hope you have the basic idea. Let's talk about a little variation. So it's very easy to tell if a graph has an Euler circuit or not. A little variation here, which is also pretty easy. Variation. What about a path using each edge once? And I will just say, but it's not a circuit. All right? A path which uses every edge once, but it's not a circuit. Can we talk about how do you know if such a thing exists or not? For example, if I have a graph like this, actually in this one you can make a path that covers every edge, but it won't be a circuit. For instance, I can start here and go like this around the top, and then around the bottom, and then around the middle like so, and end here. All right? That one uses every edge, but it's not a circuit. There's a name for that. This is called an Euler path. All right? It goes around the whole thing. It covers every edge once, but it doesn't start where it finishes. It's not an Euler circuit. All right? How do you know when such a thing is possible? It's natural to think of it in terms of the degrees. If you look at the degrees in this case, I'm just going to redraw that picture. It's like this, with dots in the middle. The degrees here are mostly 2, I would say. That's a 2, that's a 2, that's a 2, that's a 3, that's a 2, that's a 3, a 2, a 2, and a 2, right? Those are the degrees of the vertices. And when I think about even versus odd here, they are all evens except for those 2 3s. If you think of this in terms of leavings and arrivings, it means everything will work out great except for by these 2 3s. They will either have one extra leaving or one extra arriving. It's not a coincidence that those were the starting and ending points here, all right? When I did this thing here, the fact that this was the starting point meant it left more often than it arrived, and the fact that this was the ending point means it arrived at the end but didn't leave again. So this Euler paths exist as long as there are 2 odds and everything else is even. And those two odds will be the starting point and the ending point of your path. That's the idea for Euler Path. So I'm going to write that, what I just said, I'm going to write as another theorem. And Euler figured this out too. So an Euler path exists when all vertices have even degree except two odds. All right? And that's what happened in that example right there. If they're all even except two odds, then actually you can make an Euler path. That is, it uses every edge one time. But it's not a circuit. So an Euler path exists when all vertices have even degree except two odds. And I will just say the two odds are the start and the end of the path. Right? The fact that they're odds means one of them can have an extra departure, which will be the starting point, and the other one can have an extra arrival, which will be the ending point. All of the other ones have the same number of arrivings and departures. All right? This is how you know if an Euler path exists or not. So maybe I will just look, can we look back at these examples that I was looking at before? This one right here, it has no Euler circuit because it has some odds. It does have an Euler path though, because it only has two odds. So this one here, I'm going to copy this down. This one does have an Euler path, does not have an Euler circuit. And can I make the Euler path here? Maybe, can you try to do this one on your dear paper? Make an Euler path on that graph. Decide where you should start. You want to cover every edge in the whole graph and end up somewhere different from where you started. That's what an Euler path means. This has two odds, so an Euler path exists. I'll give you a moment. See if you can draw a path which covers every edge. Remember I said before you should start, the two odd ones are where you should start and finish. I mean, you should start on one of the odds, and you should finish on the other odd. That's how it must be that way if this is going to work at all. It looks like some people have figured it out. Here, I'll tell you how I did it. You better start at one of these threes. Maybe I'll start at the one on the left. And then it's not so hard to make this work. I think you can pretty much do what you want. Just don't repeat any of the edges. So I'm going to come around the top, maybe around the bottom now. And then across the middle like that. And finishing right there. All right? Something like that. There are other ways you could have done this. In this example, it's pretty hard to get stuck, actually. I think you could go pretty much any way you like, and this will work out. All right? An Euler path. So maybe to summarize, we got 15 minutes. I have one more interesting thing that Euler figured out. But to summarize so far, an Euler circuit exists if there's no odds. An Euler path exists if there's two odds, right? What about if there's even more than that? Well, if there's more than two odd vertices, you really can't do anything, any kind of Euler anything. You're going to have to repeat some edges in order to cover them all. What about if there's only one odd, though? This is an interesting kind of situation in the middle, right? What if there's only one odd vertex? What if there's only one vertex with even degree? odd, sorry. What if there's only one vertex with odd degree? What happens in that case? If there's 0 odds, there is an Euler circuit. If there's 2 odds, there's an Euler path. What if there's only one odd degree vertex? Maybe, can I give us, let's take until 1140. Can you just draw yourself an example of a graph which has only one odd degree vertex? And then I want to talk about what can happen. Oh, we've only got 3 minutes until 1140. See if you can draw a picture of a graph with only one vertex of odd degree. Remember, the degree is how many edges touch the vertex. I suppose you could look back at all the examples we've ever done and see if you can find one, or you could just try and invent an example. This is actually what I'm drawing right now. It's not an example, but see if you can play around with it and make a graph having only one vertex of odd degree. You have 2 more minutes. I'm going to walk around and see how you're doing. It does, yeah. This is not, what I drew there is not a correct answer to this question because it has 2 odd vertices. I want you to draw one which has only one odd degree in it.
Literally the exact same thing.
So the 4 points of the square would always choose another one. That's a 3. The extra one needs to be the end of that.
It's 5.
I am first semester last year.
No, I know. I'm just trying to figure out.
I literally dropped it. I don't even understand.
All right, it's 11:40. Anybody work this out? I hope that you struggled a little bit. You only struggled for 3 minutes. This is impossible. It turns out it's not possible for a graph to have only one odd degree vertex. And this is actually another thing that Euler realized. Here's why. It's actually not so hard to tell why this is impossible. It's because you will realize this if instead of thinking about it in terms of individual degrees, what do you get when you add up all the degrees? In this example, if I add them all up, I guess I get 8, right? If you add up all the degrees, this is actually called Euler's theorem about the sum of the degrees. If we sum the degrees, this actually is not a super deep fact. It would probably occur to any of us if you thought about it for long enough. If you add up the degrees, we get 2 times the number of edges. Check it out. In this example here, I have like 1, 2, 3, 4 different edges, right? And if you add up all the degrees, it adds up to 8. This is not a coincidence. Any graph that you ever draw, the total sum of the degrees equals 2 times the number of edges. Does anybody feel like that should be true, or why that might be true? The total number of degrees, the total sum of the degrees is related to the number of edges. Remember, the degree is how many times an edge touches each vertex. The relationship between the number of edges and the sum of all the degrees is something like every edge has 2 ends to it, right? And so that means that every time one of these edges meets there are 4 total edges. That means there are 8 total ends of edges. And those ends of edges got to end up somewhere, and they contribute to those degrees, right? When you are adding up all the degrees together, you're basically adding up how many total ends of edges there are, and that's always 2 times the total number of edges. So that's why this is, I'm going to write this as a theorem. So this is called Euler's sum of degrees theorem. This doesn't really have a better name than that. And it says the sum of the degrees, it says what I just said. The sum of degrees equals 2 times the number of edges. All right, one thing that this means is the sum of the degrees is always even, and that's why you can't have just one odd degree vertex. Because if there was only one odd degree, then when you add up the sum of the degrees, it would end up being odd, and that's not allowed. So the sum of the degrees equals 2 times the number of edges. I will say, therefore, the sum of degrees is always even, right? And that's why you can't have a graph which has only one odd degree, because then when you add all the degrees up, you would end up with an odd, which is not allowed, because the sum of the degrees is always even. All right? In our remaining 7 minutes, I have an interesting real-world example that has to do with the NFL. Can you believe it? I actually know very little about the NFL. I looked this up, though. This is kind of a famous example among graph theorists. They love to talk about this time when the bozos in the NFL made some kind of error that has something to do with graph theory. So this is a real example about the NFL. So my understanding, like I said, I'm not an expert. I'm sure many of you know more about the NFL than I do. The NFL for a long time had 2 conferences, which I believe is still true. But at the point in time that this story occurred, there were 13 teams in each, which I believe is not true anymore. And there were the rules for the league. They decided at the beginning of one year, they decided like how many games we're going to actually play, and the NFL decided that we would have each team plays 14 games. And the rule, this was the idea behind the schedule. It was like before they made the specific schedule, they had to decide how many games we're going to play. They said each team should play 14 games, which would consist of 11 in conference and 3 outside conference. So they, the guys with the suits decided that this would be the way that the schedule would go, and then they gave it to some people to actually make the true schedule about deciding exactly who's going to play who or whatever. It turns out this arrangement described right here, this actually is impossible to do for graph theoretic reasons. This is not possible because of the sum of degrees formula. So this is impossible. If you make a graph out of this, so consider a graph. This is something that the guys in the suits did not think about. I think they just made the rules assuming that they could choose anything and it would work out. This is mathematically impossible though. So consider a graph of the 13 teams in a conference and 11 in-conference games each. Right, so you make your graph with the 13 teams and then you put an edge between any teams which are playing against each other in a game. And what would that look like? It looks like each vertex has 11 edges, right? Connecting each vertex to all of the games that it's playing, all the other teams that it's playing. Each vertex has 11 edges, so actually each vertex, each degree is 11, right? And that means if you add up all the degrees, the sum of the total degrees would be, 11 plus 11 plus 11, 13 times. So the total sum of degrees is 11 times 13, right? There are 13 teams, and each one is degree 11. So this is 11 times 13, which is 143. And that is an odd number. This is impossible. Euler's theorem says that the sum of the degrees is always 2 times the number of edges. And in fact, so in particular, it must be even. It's not allowed for the sum of degrees to be odd. So this is odd, which is impossible. All right. So the moral of the story is if you want to make some kind of scheduling diagram for your teams to play each other, you can't just make it however you want. There are actually some kind of like mathematical restrictions. It is not possible to just make up whatever you want and expect it to work out in real life. So apparently when this happened, they told some people, okay, make us a schedule, which looks like this. And eventually the people said, I don't think we can do that. It's true. There are some weird mathematical principles at work there. All right. I think that'll do it for today. Next time we're going to do a lot more specific examples.